Welcome to this explainer. Today, we're doing something a bit different. We're going to look up into the sky and decode the literal, invisible architecture floating all around us. We are taking a deep dive into GSM networks. Now, instead of just thinking of this as invisible radio waves, I want you to imagine it as a highly regulated, unbelievably fast highway system. Millions of people all driving on the exact same roads at the exact same time without ever crashing into each other. How does that actually work? Well, let's dive in and find out. Here's our roadmap for today. We'll kick things off with the digital mobile revolution, decode the GSM spectrum, and master time separation. Then we'll look at quality, control, and idle mode, explore the art of handovers, and finally look beyond GSM. All right, Section 1, the digital mobile revolution. Let's set the stage for what GSM actually achieved. To really grasp GSM, you've got to understand that it was basically the big bang of the 2G mobile revolution back in the early 90s. Before this, 1G networks like NMT and AMPS were purely analog. They pretty much just carried voice. But users were slowly wanting to send data, like early faxes, over mobile connections. So GSM came along as one of the very first truly digital systems. Because it was digital, it meant all communication was just data. Voice was converted from analog into data and back again, which suddenly unlocked encryption, way better security, and most importantly, allowed pure data to just fly through the air. So let's lock in our baseline definition here. GSM, or Global System for Mobile Communication, is a 2G digital cellular standard. Its core innovation, the real game changer, is how it divides the frequency spectrum and uses time slots so multiple users can share the exact same physical space. Keep that in mind because we're about to look at the actual highway this data travels on. Moving right along to Section 2, decoding the GSM spectrum. 200 kilohertz. Keep that exact number in your head. If we're using our highway analogy, a 200 kilohertz radio channel is your fundamental single lane. Everything in this system revolves around the bandwidth of this one single lane. So how many lanes do we actually have? Exactly 124. The standard GSM 900 frequency spectrum is carved up into 124 of these 200 kilohertz radio channels. Now, check out how FDD, frequency division duplex, creates two totally separate directions of traffic. You've got your uplink band, which is your phone talking to the tower, operating between 890 and 915 megahertz. Then, completely separated from that, you have your downlink band, the tower talking back to your phone, operating between 935 and 960 megahertz. They are separated by exactly 45 megahertz. We call that the duplex distance. Basically, it means your phone is never trying to shout and listen on the exact same frequency at the same time. Which brings us to Section 3, TDMA, and mastering time separation. We have our frequency lanes, sure, but now we need the carpool lanes. Here is the ultimate million-dollar question. If you only have 144 lanes, but literally thousands of people in a city are trying to make calls, how on earth do 8 people talk on a single 200 kilohertz channel at the exact same time without talking over each other? Well, this is the absolute genius of TDMA, time division multiple access. On top of frequency separation, GSM uses time separation. Using time division duplex, or TDD, the network takes that single 200 kilohertz lane and slices it in time into 8 precise slots. Users are offset in time. You take a turn, the next person takes a turn, and so on, but it happens so unbelievably fast you don't even notice. You're sharing the frequency, but you completely own your specific fraction of a millisecond. Let's put one of those single time slots under a microscope. It is incredibly brief, just 0.577 milliseconds long. But inside that tiny window, it holds a highly structured frame of exactly 156.25 bits. It starts and ends with tail bits. Right in the middle, you get 2 blocks of 57 bits of coded data. That's your actual voice or text. Between those blocks, there's a control bit and a 26-bit training sequence, which helps the receiver equalize the signal. Finally, at the very end, we have a guard period. That guard period is about 8.25 bits long, and it's absolutely crucial. It prevents bursts of data from different phones at varying distances from crashing into each other at the base station. Because of all this necessary structure, the maximum net bit rate for your actual data per time slot is 13 kilobits per second. All right, Section 4, Quality, Control, and Idle Mode. Let's talk about the cops and way stations that monitor all this digital traffic. Okay, I know GSM is packed with alphabet soup, so let's break down a quick cheat sheet. You have CI, or cell identity, and BSIC, which identify the specific cell tower you're connected to. Then there's the BCCH, a broadcast channel constantly pushing out system info. But I really want you to focus on the bottom two, RX qual and RX level. These dynamically measure your radio connection. RX qual measures quality, specifically the bit per error rate, on a scale of 0 to 7. 0 is perfect. If you hit 7, your call is probably dropping. Now, RX level measures the raw signal strength from 0 to 64. Let's do the math on this really quickly. It starts at a baseline of -110 dBm. So if you have an RX level of 30, you add 30 decibels, giving you a solid signal of -80 dBm. Your phone and the network are constantly running these numbers. But what's your phone actually doing when you're not on a call? It enters idle mode. Think of this as your car resting at a way station. You aren't transmitting, which saves your battery, but you're not entirely asleep either. Your phone evaluates its surroundings and camps on the strongest cell. It continuously monitors the system information, and most importantly, it listens to the paging channel. It's basically just waiting to hear if someone is trying to call you, so it can instantly wake up and respond. And overseeing this entire operation is the base station controller, or the BSC. Think of it as the ultimate traffic cop. It takes all those RX qual and RX level measurements from your phone and from the tower, and it makes split-second decisions. It controls power levels, literally telling your phone to shout louder or whisper to save battery. It manages timing advances to keep your slots perfectly aligned, and it can even order your phone to hop frequencies to maintain signal margins and dodge interference. Let's move right into Section 5, the art of handovers. These are the highly complex intersections where moving phones switch network jurisdictions. Now, a handover isn't just about your signal dropping. It's way more sophisticated than that. There are actually 6 advanced triggers in GSM. First, the intra-cell handover. If your signal quality drops but there's no better tower nearby, the network might just move you to a different channel on the exact same tower. Second, we have level-triggered handovers, where the network passes you to an adjacent cell if your signal margin drops. Third is the quality-triggered handover, which acts as a safety net if your bit per error rate gets too high. Fourth, distance-triggered handovers, based purely on timing and range. Fifth, and this one is super cool, speed-triggered. If you're zooming down a highway, the network detects your speed and stops your phone from camping on a tiny indoor cell that you'll just pass in 2 seconds anyway. And finally, number 6, traffic-triggered. At a predefined traffic level, if one cell tower gets too crowded, it will literally hand over calls to adjacent cells just to offload the traffic. Finally, Section 6, Beyond GSM. Looking at DCS and UMTS. Because, as you might guess, that initial 900 megahertz highway eventually got incredibly congested. First, they expanded 2G with DCS, Digital Cellular Systems. This basically took the exact same GSM rules and applied them to a higher frequency, the 1800 megahertz band, giving operators way more 200 kilohertz lanes. But soon, we needed real broadband data. That led to UMTS, or 3G, utilizing WCDMA technology. Instead of slicing time into slots like GSM, WCDMA gives everyone the entire frequency at the exact same time, but separates users with really complex mathematical spreading codes. This allowed for massive leaps in data transfer rates and overall network capacity. But I want to leave you with a final provocative thought. By allowing everyone to share the exact same frequency at the exact same time in 3G, we introduced a totally new problem, orthogonality degradation. Essentially, as signals bounce off buildings and arrive at different times, those mathematical codes start to blur together, creating their very own form of interference. It just goes to show, every time we build a wider, faster digital highway, we have to invent entirely new rules of physics and engineering to manage the traffic. That is all for this explainer. I really hope this helped decode the airwaves around you.